These first two sections of chapter 4, we're just going to talk about the characteristics of exponentials and logarithmic functions themselves and kind of some fun facts about them that you're going to see recurring over and over again throughout the 5 sections we cover in this chapter. So first things first, let's go over the shape and characteristics of exponential functions. I'm going to be using blue to talk about exponential functions today, just as a heads up, and I'm going to be using purple later on for logarithmic functions, just as a little preview. Exponential functions are functions where the variable is in the exponent. So they're typically written as b to the x power, where b is any base that is not equal to 1 and is greater than 0. Typically, that's a number like 2 or 3 or 5 or maybe 1/2. These functions model a lot of real-world scenarios, which includes population growth, growth of pandemics, radioactive decay, and anything that increases at a percentage each time instead of a particular rate. The way that the graphs look, we should be pretty familiar with these. This is what an exponential function looks like. Just as a bonus, would this one be considered growth or decay? Okay, so we know a little bit about this because it's going up, so it's growing. It starts at a particular number if we have time intervals, so we have an initial value, and then it goes up. But we're going to talk more so, less about a real-world scenario for a second and more about the function itself and go over the characteristics of b to the x power. Now, an exponential function has a domain of all real numbers, and this makes sense because if we're looking on the left, there's an arrow extending out to the left, it's flattening out, and there's an arrow on the right side. Yeah, it's going up, but it's going up and out. So that means we're extending from left side to right side the entire time. Its domain is all real numbers. The range of this function, though, is interesting. If you notice, the range is not all real numbers. The range has a boundary at the number 1. This comes from the fact that there is a horizontal asymptote at 0. I think I said the number 1 just a second ago, but it should be the number 0. So horizontal asymptote at y equal to 0. The graph will not go below the number 0. It is a boundary for a bounded below characteristic of this graph. For any non-transformed function, non-vertically transformed function, the y-intercept is going to be 1. So if you'll see, anything raised to the 0 power is 1. So unless we've transformed this graph in some way, we have the answer is 1. And there is no x-intercept for a non-transformed graph because we have that boundary line happening at the x-axis for any non-transformed graph. You guys kind of thought about this earlier. If the base is bigger than 1, then the function looks like this. And you guys told me a second ago that was growth. If the base number that we're using is between 0 and 1, this is what it's going to look like. And what word did we use to describe this before? Decay. So it's a decreasing graph showing us exponential decay. So that depends solely on what the base value is that we're using there. This function is 1-to-1, which if you don't remember what 1-to-1 means, that means it passes both the vertical line test and the horizontal line test. So that means that its inverse would also be a function. So it's a function with an inverse that's a function. And like I pointed out to you earlier, y equal to 0 is a horizontal asymptote for this graph. It has a boundary line at the bottom or potentially the top of the function. It's going to be bounded on one side. Now, all of these characteristics are the characteristics of the non-transformed version of the exponential growth or decay function. If we go to transform it, these characteristics can change. So for example, we're going to transform 2 different graphs down here and just see what that does to the different characteristics. The first one we're going to graph is, this is a base 3 function, so 3 raised to the x power. And we're going to use the graph to obtain the graph of 3 to the x plus 1. So our questions when we talk about transformation should always be, is that transformation happening on the inside or the outside of the function? Is that plus 1 happening on the inside of the function or on the outside of the function? Inside. Since the inside where the variable is the exponent and that plus 1 is in the exponent, we would say that this transformation is happening inside the function, which means does that affect the inputs or the outputs? Inside is inputs. So we're going to be changing the x values, and we're going to be changing the x values of this graph specifically by doing -1. Remember, horizontal, inside, opposite. So if you see +1, you actually subtract 1 from everything. So my first coordinate point is at -1, 1/3. I'm subtracting 1 from the x value, which means this is no longer -1. What's this number going to be? We're subtracting 1. So -2. From -1 minus 1 is -2. Ooh, it's been a whole fall break, hasn't it? Okay, we take the second coordinate point and we subtract 1 from the inputs. This changes from 0 to -1. If we take this coordinate point, this is the last one that's plotted for me. It's 1, 3, but instead, what should I be plotting? Subtract 1 from the x, 0, 3. Okay, that's all we have because I only had 3 dots on my graph to begin with. So we're going to play connect the dots here. Boom, boom, boom. Move this all the way up. Ooh, that was a horrible. Let me try that again. It's embarrassing. Okay, so let's see what characteristics of this graph changed when we did a horizontal translation of this graph. Did the domain change? No, it's still infinity to infinity. Did the range change? No, the range is still the same. The next thing on my list was the x-intercept and y-intercept. Did one of those things change? Yeah. Ooh, what changed? The y-intercept changed. So that's interesting that if we move something side to side, we change the y-intercept. Did the x-intercept change? No, there's still not even an x-intercept here. It's still increasing. We didn't change that. It's still 1 to 1. We didn't change that. Did we change the horizontal asymptote? No. So the only transformation change that occurred was changing the y-intercept. Easy peasy. That's moving it side to side. What if we take a different graph? This one is base 2, 2 to the x, and we're going to use the graph of 2 to the x to obtain the graph of 2 to the x minus 3. Is that transformation appearing inside or outside? Outside. So is it going to affect the inputs or the outputs? Outputs. So the output one, you just do exactly what you see, which means we're going to take all of the outputs and we're going to subtract 3 from the outputs. Okay, if I go to do that, the first, we'll start over here because it's just easier. If this was 2, 4, and I subtract 3 from the outputs, where should that coordinate point be? 2, 1. Okay. If this was at 0, 1, where should the new point be? Wait, how many am I moving it down? 3. So 1 minus 3 is -1. That's why that didn't make sense. That's not the coordinate point 0, 2, 0, 1. Oh my gosh. I'm feeling that it's a Monday as well. This is the coordinate point 1, 2. Now when we subtract 3 from it, it makes more sense that it goes to -1. I'm here now. I got it. This is the coordinate point 0, 1. And when we transform that one, where should it go? That makes way more sense. No wonder everybody's looking at me like I was crazy. If we transform the other ones, they're all fractional output values. So just do your best. The -1, 1/2 will go down to -2. No, sorry. -1, wow, my brain is not braining. -2.5. And then the next one kind of follows down there. We can play connect the dots. Okay, let's talk through the characteristics of this new function to see what has changed, if anything. Did the domain change? Nope. Okay, still all real numbers. Great. Did the range change? Yes. So because we moved this thing up and down, there's now a different lowest value here. We had a horizontal asymptote at y equal to 0. Where is our horizontal asymptote now? -3, which means our range has changed. the range has changed to being -3 to infinity, which also then means that the horizontal asymptote has changed, since that is affecting the range. There's two other things that have changed here. What is it? The y-intercept changed. It went from 1 to -2. What else changed? There's actually an x-intercept now. Interesting. So this transformed graph, if we're just moving it left and right, only one thing changed. But if we move it up and down, 4 things changed when we transform this graph. So be on the lookout for any transformed graphs, because you can't automatically answer the things from the box necessarily. That's for an untransformed version of the graph. Okay, so we get the shape of these functions, the characteristics are there, but what we want to do is we want to start being able to answer some real world questions, and we need to introduce what's called the natural number, which you may remember from a previous course. The natural base E, or the natural number, also if you're Googling around for help, this is sometimes referred to as Euler's number. And yes, that's pronounced Euler. I think he's a German guy. I meant to Google that from last class now. Forgot what his nationality is, but that's Euler's number. He's the mathematician who codified this for us. The irrational number, symbolized by the letter E, appears as a base in many applied exponential functions. So this number E is approximately equal to 2.718 or 2.72. But we want to be super accurate when we use this number, kind of like when we use pi. So our calculator has a way for us to use the E button the same way there's a pi button. So if you look on your calculator, above the divide key, you see how there's a blue little E there? We need to use that for E. But there's also a second option. If you look above the LN button, there's a blue E to the X. You can also use that one. So you get two choices of where your button that you're using is there. But we just need to make sure we can utilize this button for when it comes up in real world questions. So we have this example about the gray wolf population. The gray wolf, which is a breed of wolf, undeservedly acquired a reputation as an insatiable killer in the the 19th and early 20th centuries. So an estimated 2 million wolves were shot, trapped, or poisoned. By 1960, I know, don't worry, there's a hope. Because by 1960, the population was reduced to 800 wolves only. We then place them on the endangered species list. So the figure below shows the population in 2 recovery areas after the gray wolf was declared an endangered species. We also have an exponential function, 1,144 times e to the 0.0325x, that models the gray wolf population in this Western Great Lakes area for a certain number of years after 1978. So the question that we have here is according to the model, and when we're talking about a model, we're talking about the formula. According to the model, what was the gray wolf population rounded to the nearest whole number of the Western Great Lakes in 2018? Now, we are not plugging the year 2018 into this formula because the x value is years after 1978. How many years after 1978 was 2018? How many years was it? 40. So the x value that we're going to plug in is 40. So we would do f of 40, and we're just plugging that straight into our calculator. 1,144 times e to the 0.0325 times 40. And when we come back from lunch, we'll discuss what we get from that, and we'll answer question B. Now that we've got that typed in, the calculator is going to spit out to you approximately 4197.675. Yes? Now, this is going to be the kind of chapter where you really do need to pay attention to the little instructions when we get to the homework that tells you how to round. This one specifically said to round to the nearest whole number. So we're going to answer this as 4,198 wolves, which is nice. That means the population is growing. Hooray! Now, of course, we developed this model based on predictive values. And then the scientists and ecologists out in the Western Great Lakes area actually, went and counted the number of gray wolves that were in this area, because that's what we were studying. And they got this number when they straight up counted the wolves. So if we're comparing our model, so the number we got when we plugged a number in, to the actual data we had, let's just compare those numbers for a second. The model got us 4,198. The actual data from the actual scientists counting gray wolves was 4,222. So did our model over or underestimate that number? Underestimate. I mean, it's not horribly an underestimation because it's still really pretty close, because it only underestimated by 24 wolves, which is pretty good, but still not perfectly accurate to what happened in real life. The second real life scenario that we're going to introduce to you that uses an exponential function, and specifically the base e, is money. Usually gets people's attention. Nope, we're all still in a lunch fog. Okay, compound interest is how banks work. Do we know the basics of how banking works? So you tell a bank, here, hold this, and it's money. And the bank says, thank you for letting me hold on to your money. I'm gonna do stuff with this money while I'm holding it. But then because they're using your money, they have to pay you interest, since you're asking them to hold this and they're getting to do something with your money. Now, compound interest comes in two particular ways. The more common one is called one that's compounded a number of times per year. That's this formula here. The P stands for the principal investment. That's what you told the bank to hold on to. The R is the rate as a decimal. The N is the number of times something is compounded per year, and the T is the number of years. The second way compound interest is used is for continuously compounding interest, and that formula is the amount in the account would be equal to the principal investment times E raised to the RT power, which means the same thing. Principal, how much you started with, the rate, and the number of years. So what's important for us to know just as human beings as we get older is how to determine what sort of investments are good investments. So we're going to see in the example 3 here, it's going to give you two options, and we're just going to determine which account would return the most money to us, which amount would have the most in it at the end of a particular number of years. So you decide to invest $8,000 for 6 years, and you have a choice between two accounts. The first one pays 1.20% per year compounded monthly. The second pays 1.19% per year compounded continuously. Which one would be the better investment? So we're going to split our notes into two sides. One of them is going to be account 1, and the other one is going to be account 2. So the first one is the one that's going to be compounded monthly, so we'll use the top formula. The second one is the one that will be compounded continuously. If we take the individual pieces we got from the problem, which would be that we are finding the amount in the account when the principal investment is $8,000, the rate is 1.20%, but I don't want to use that as a percentage. How do you change that to a decimal? Move the decimal 2 spaces by the Dr. Pepper rule. This becomes 0.0120. We need to also know the N and the T. T is 6 years, because they told us that's how long we're investing this for. But we need to figure out what the N is. N represents the number of times something is compounded per year. And if ours says that it's compounded monthly, how many times is that going to happen in a year? 12. So that's going to be the one tricky thing, is that you have to look for the kind of compounding it is so you know the N value that you're using. But with all of these things, that's all of the information I needed to plug into the formula. We are finding the amount in the account. If we plug $8,000 in as the principal, we'll do 1 plus the rate, 0.012, divided by 12, raised to the 12 times 6 power. Just plugged everything in exactly where it goes in the formula. There are no more variables left here, so once you have that written down, you're going to turn to your calculator, and in one turn, you're going to get all of that in there. You're going to use the parentheses, you're going to use the fancy fraction, you're going to use the exponents. We're going to calculate how much money would be in this account if we put $8,000 there and did nothing else for 6 years. I'll write it down just because it's a larger number. We should have gotten that the amount in the account is 8,596.93. Is that what you guys got? I chose to round to 2 decimals because this is representing money, so you're going to round to 2 decimals, right? So that means we gained $596.93 by doing nothing. All we told the bank was to hold this money, and they paid us for it. Nice. Let's check the second account, because this is a different setup. We want to see which one is the better deal for us. If I'm just going to list out all the things I need an A, a P, an R, and a T. Remember, E is a number, so we don't have to plug something in for E. It is a number. We're still finding the amount in the account. The principal is still $8,000. The rate, however, is 1.19%. which if we change that to a decimal is 0.0119, and then the time is still 6 years. This is for continuously compounded interest. That's the key words you're looking for there, continuously compounded. If we plug all of this into that second formula, we are finding the amount in the account by doing 800 times e to the 0.0119 times 6 power. P, I didn't put enough zeros. That's embarrassing. I'm gonna fix it. Ooh, that looks horrible. See how much money would be in the account now with this type of investment scenario. We should have gotten that the amount in the account for account 2 would be 8,592.09. So just by looking at 6 years worth of investments, which one is technically the better investment? Account 1 is the better investment, not by much. And all of this would change if you planned to leave this money in the account for 12 years. You'd have to redo these numbers, changing the time to 12 to see if that's still the better investment. So when you go to open bank accounts or investment accounts, you do want to know what you're investing with and for how long. So account 1 is the better investment. Does all that pretty much sound familiar? Have we heard these sorts of things before, potentially? Great. Exponential functions are something you've covered in multiple classes over multiple years. A type of function you may not have covered nearly as much in a previous course is called a logarithmic function. The logarithmic function is the inverse function of the exponential function itself. So we said earlier that an exponential function is 1-to-1, which meant that its inverse is a function. Here's its inverse. A logarithm is defined as follows: f of x equal to log base b of x, where the b for the base can change to a different number, but we're going to make sure we pronounce it right. That's log base b of x. Base b of x is how you'd say that. And now if you're looking at these graphs we have here, you're like, there are way too many graphs shown on this little screen right here. Great point. Let me point out to you what this is. I'm going back to blue on purpose. This is an exponential growth function. That's from what we learned about before. If we take that function and reflect it over the diagonal line y equal to x, meaning we're getting its inverse function, we get the logarithmic function log base b of x. They are reflections over the line y equal to x. If we look at the shape of that logarithm, you can see that it extends up and down like the whole graph, but like there's a barrier on one side. Keep that in mind. The second graph here is just trying to show you what the reflection of an exponential decay function would look like. That part is exponential decay. That's what we learned about on the first page. And if we flip that over the reflection line y equal to x, this is what the logarithm would look like. Again, this logarithm extends up and down the whole way, but it has a barrier on one side. If we remember from when we talked about inverse functions in chapter 2, 3? Chapter 2. It was in chapter 2. Chapter 2, we talked about inverse functions, and we said that the inputs and the outputs switch. They reflect over the line y equal to x. In fact, all of their information switches. I'm going to leave mine right here, but I want you guys to flip back to this box for exponentials on your notes real fast. So look at the box where it describes this stuff for exponentials. You're looking at a box that says the domain is from negative infinity to infinity and that the range is from 0 to infinity. Yes? Look what's up on the board now. What has happened with the domain and range? They flipped. Oh, they're inverses. You switch the x's and y's, so you're switching the domains and ranges. What else has like switched from that box to the box that I'm showing you on the screen? The x and y intercepts. There was a y-intercept on yours. Now there's an x-intercept. There was no x-intercept on yours. Now there's no y-intercept. Those switch. There's one more thing that switches. Yours says that it's a horizontal asymptote, and mine says vertical asymptote. Again, the letters switch. This makes sense, but okay, you can switch back to my page now. If we look at all of this information, comparing it to these graphs, we see that the domain has this blockade right here. It has a number that it can't go past on the x value. That is, in fact, the vertical asymptote for that graph. That's where this number is. So we could draw that in like we did for our rational functions with a dashed vertical line that are the blockade for the purple graph. Not the blue one, the purple one. Logarithmic functions are shaped differently. They're reflections over that line, and they have asymptotes that we have to make sure we are aware of. Not horizontal this time, but vertical. Since we now have these vertical asymptotes, we have changed the domain of the function. It is no longer all real numbers as an automatic answer for what the domain of this function is. We have 3 functions in general in life that have restrictions to their domain. The first one is the rational function. You guys know that that denominator cannot be equal to 0. We also learned previously about the square root function. What's not allowed to be put underneath a square root? Negative. So we have to have the radicand greater than or equal to 0. In the notes where we learned these things in chapter 2, there was a box that says something about logarithms, and it said, hang on, we'll learn about this in chapter 4. It's chapter 4. Any logarithmic functions cannot have 0 or a negative number as its argument. So we set the argument, which is a fancy word for things inside that parentheses, just simply greater than 0. Since we have this blockade at 0, we can't be equal to 0 and we can't be less than 0. The stuff inside a logarithm must be greater than 0. Again, just so I write this word down, the stuff inside the parentheses is called the argument of the logarithm. So we're going to set the argument greater than 0. That's what you're going to hear me saying over and over again. And I'm meaning the stuff inside the parentheses has to be greater than 0. And this comes from that vertical asymptote, which came from the horizontal asymptote of the exponential function. So if we're just trying to determine the domain of a function, right? Let's just look and see what we would need to restrict these 2 functions by so that we don't break the function by its domain. So we're going to take the argument. The argument is just the stuff inside the parentheses, We're going to say x plus 3 must be greater than 0 if we're finding the domain. One step to solve here, what is it? Subtract 3 from both sides. We're saying that all of the values I can use are everything that is bigger than negative 3, which means I would say from negative 3 to infinity. Again, for the g of x function, we're just saying that the argument, the stuff in the parentheses, must be greater than 0. We know this. This is a fact for domains of logarithmic functions. We would first start solving this by subtracting 7 from both sides. And then do what to finish solving for x? Divide by -1, but your spidey senses are going off because what else do you do? Flip the sign. Nice. So this becomes x less than positive 7. So we can use any number on the number line as long as it is less than 7, which means we are going from negative infinity to 7. Those are all the numbers that are less than 7. This completes the 3 of the only types of functions that have a domain that is not all real numbers. Rational, square root, and now logarithm. One of the skills we're going to need to be good at later on, especially in these chapters, is utilizing what's called the log loop. You may have seen this before, but I'm probably going to teach it a bit differently from you. The log loop is a way to change from exponential form, that's what this one is, exponential form, to logarithmic form. Since they are inverses of each other, they're equivalent, just written in different forms. So we need to be able to go back and forth between these two forms. What we're going to do is rely on the fact that we understand the concepts of inputs and outputs really well. The base of an exponential is the number that has an exponent. The base of a logarithm is the small number next to the word log. Do you see how the base is b and the log has a base b, meaning the base did not change? The loop comes in when you switch the inputs and the outputs to go from one form to the other. If we are writing an exponential as a logarithm, whatever was the input becomes the output. Whatever was the output becomes the input. And vice versa for logarithms. So I have 6 problems for us to try here where we are switching them into their equivalent but opposite form. I'm going to do A and D, and I'm going to let you guys do the rest of these. But if I was writing question A in its equivalent form, it is already a logarithm, so I'm going to write it as an exponential. What's the base of this logarithm? 5. So that's going to become the big number that is going to be equal to, raised to a power and equal to something. After that, I have to switch what was the input and the output. What is currently the output for this equation? 2. That becomes the input. What was the input a second ago? Becomes the output. We've looped them. Inputs and outputs switch since they are inverse functions. For D, and I'm switching down to D, that one is an exponential, and I want to write it as a logarithm. What's the base of that exponential? 12, so I'm going to go log base 12. Then I need to figure out what the output and input should be. What was the output when it started here? What was the output? X, that means X is going to go on the inside, and this is going to be equal to 2. So again, base stayed the same, and I just changed the location of this. Base stays the same, and I just changed the location of these. It's looping them from inputs to outputs and outputs to inputs. I want you guys to finish the rest of these on this page. B, C, E, and F, please. Okay, I've got the first 3 up there if you want to check. I want to do this last one with you guys. So again, the questions you always ask yourself, what is the base? Base should stay the same, and you loop the input and output. For this last one for letter F, what is the base? E. So this is going to be log with a base E, and then we're going to switch the input and the output. What was the output when it was printed on the paper? That is now the input, and it's going to be equal to basically whatever's left, which is Y. Now some of you, your spidey senses might be going off about this answer. Hold on to it. We'll get to it later. The reason that we focus on this log loop is because, one, in a couple chapters or a couple sections, it's going to help us solve some equations. But also, when combined with our exponent rules, maybe specifically some of the exponent rules that you've forgotten, so they're here for you in case you need that, we are going to be able to evaluate simpler logarithms. This is really going to be nice if you know your power families, which means you know your multiplication tables. If not, you got a calculator there to help you. What we are going to do to evaluate a logarithm, because this is a math fact. This would be similar to me asking you what is 5 times 5. You know that one. It's 25. Same way, we can just know what log base 2 of 16 is. But we're not good at it because we have not been thinking in terms of logarithms for very long. So instead, we're going to set this equal to x, basically like a placeholder. And I'm going to log loop this because I'm probably going to be able to answer this question easier if it's an exponential than if it was a logarithm. So if we loop this, what is the base? 2, and it should be raised to what power? X equal to 16. Okay, well that's something that's a little bit easier to answer. 2 to what power is 16? 2 times 2 is times 2. 8 times 2. 16. How many fingers do I have up there? 4. 2 to the 4th power is equal to 16, which means log base 2 of 16 is 4. We can evaluate this logarithm without having to actually think in terms of logarithms. We can convert it to an exponential and answer the question in power families. Now, if we don't know our multiplication table, that's a different story. Of course, I'm not going to make it be that easy every single time. What if we have a question like B? What is the base here? 7. Okay, so log base 7 of 1 over 49. That'll be 7 to some power being equal to 1 over 49. Maybe let's start a step back. 7 to what power is equal to positive 49? 2. But how do I get that 49 to be in the denominator? There is an exponent rule most people forget about. Look at this guy. It says if you want something out of the denominator or into the denominator, you make its power negative, which means 7 to the negative 2 power is equal to 1 over 49, because it moves it to the bottom. Log base 7 of 1 over 49, therefore, is negative 2. Let's try a couple more. Log base 25 of 5. So the base is 25 raised to some power x should be equal to 5. How are 25 and 5 related? 25 is the square of 5. So isn't it true that the square root of 25 is equal to 5? Interesting. But I don't want a square root. In fact, if we use this property of exponents that we've probably forgotten about, and that's okay, we can change that square root to a fractional exponent. This property of square roots says that if you have a radical, then you can take the power of the base on the inside and the index of the root and make them a fraction of power divided by root. So if we're looking here, what is the power? 1. What is the index? 2. So this is 25 to the 1/2 power being equal to 5. Therefore, log base 25 of 5 is 1/2. It's all about knowing our power families and how numbers are related to each other within those power families. Now let's see if this makes sense. One more example using that same rule. Log base 2 of the 5th root of 2. Again, if we log loop this, this is 2 to some power is equal to the 5th root of 2. If we look at this rule again, it says any radical can be written as a fractional exponent. What's the power on the inside? 1. What's the index on the outside? 5. So this is 2 to the 1/5 power, which is 5 root 2. 5th root of 2. Therefore, log base 2 of the 5th root of 2 is 1/5. There are other simple properties of exponents that we're going to start going over. Basic logarithmic properties. How about that? These logarithmic properties are as follows. If you have log base b of b, meaning the bases match, automatically that's equal to 1. So for example, what is log base 7 of 7? 1. That's it. Easy property to use. If you have log base b of 1, it's always 0. So log base 5 of 1 is 0. Easy peasy. And that's because anything raised to the 0 power is 1. The next property of logarithms is log base b of b raised to some number. So log base b of b with an exponent right here. In my mind, these like cancel each other out. So I literally do that in my head. What's left? X. So log base 4 of 4 to the 5th power, what is that? 5. And if we go the other way, so now if it's an exponent raised to a logarithm, so b raised to the log base b of x, again, same thing, these kind of like cancel out, so it's just x. So if we have 6 raised to the log base 6 of 9, this is going to cancel. What are we left with? 9. It doesn't really like cancel. I should stop saying that. But visually in my mind, it goes away. So it cancels. Similar to when we learned about the base e when it comes to exponentials, logarithms also have some fancy buttons on the calculator. And they're for very widely used, commonly used logarithms. In fact, one of them is called a common logarithm. If you have a logarithm with a base of 10, logarithm base 10 is used so often it's literally just called the common logarithm, and we've dropped the 10. So if you see log with no number sitting underneath it, that's called a common logarithm. You do have a button for that on your calculator. Let's find it. It's a straight up button. It says log. Do you see it? Yes. Next to 7. You can press that, and that will evaluate a common logarithm for you, whatever you type in afterwards. The one thing I want you to notice is go ahead and click that log button. Do you see how it starts a parentheses for you? You make sure you close that parentheses before you press enter. Yes? Okay, cool. The second kind of logarithm is that logarithm with a base that's the natural number e. Log base e. It is usually expressed not as log base e, but as what's called the natural logarithm, and it gets its own button as well. Its button says ln, even though we pronounce it natural logarithm because it was created in a language that puts adjectives after nouns, unlike English. So it is the ln button. Do you find the ln button? Also click that one. Do you see what also it types in for you automatically? It opens a parentheses, so you must close it. Make sure you know that. But that will help us being able to evaluate the log and natural log without having to go through horrendous settings on these calculators to find the change of base. So let's practice. Example 8, it says the percentage of adult height attained by a boy who is X years old can be modeled by the function f of x equal to 29 plus 48.8 log of x plus 1, where x represents the boy's age from 5 to 15, and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has a boy attained at age 8? Okay. Age 8 does mean that we are plugging the number 8 into this formula because it says x is the boy's age as long as it's between 5 and 15. So all we're going to do is evaluate f of 8 from the formula that it gives me. So 29 plus 48.8 times log of 8 plus 1 because we want to know what's happening at year 8. We go to our calculator and we just straight up type that sucker in. We're using the log button on the home screen itself or on the front plate. We should get approximately 75.5670, yes? Which means if we were answering this question to what percentage, we're going to round to the nearest percentage here. So 76%. So when a child, a boy is 8 years old, he's at 3/4 of how tall he's going to get for the rest of his life, generally. But we found the log button, yes? Let's make sure we can find the other button. Example 9, when the outside air temperature is anywhere from 72 to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in that first hour. The bar on the right shows the temperature increase throughout the hour. The function f of x equal to 13.4 times natural log of x minus 11.6 models the temperature increase in degrees Fahrenheit after X minutes. Use the function to find the temperature increase to the nearest degree after 50 minutes. We are going to use 50 as our input value because X represents minutes. So if X is equal to 50, all we need to know is F of 50. When we plug this in, this is why I was making such a big deal about those parentheses, because you're going to put a 50 in that parentheses and close it before you do minus 11.6, because you are not subtracting 11.6 from 50, you are subtracting 11.6 from the quantity 13.4 times natural log of 50. So go to your calculator, type all this in one fell swoop, making sure you use the natural logarithm button. We should get approximately 40.8211. So we would return the value to the nearest degree, which is 41 degrees. Part B asks us again, how well does this function model the actual increase in the figure? Did we over or underestimate this value? We got it exactly right. Yeah, here's when X is equal to 50, and it said the increase in temperature should be 41 degrees. That's exactly what we said. So our function models the data really well. Hooray. That's nice to hear.